Hello, everyone, and welcome to Beyond Bandwidth, Leviton's podcast series where we dive into network technology's hottest topics. I am your host from Leviton Network Solutions, Roy Chamberlain. This conversation shines the light on AI data centers. In part 2 of our 4-part special edition to this series, Leviton's Mike Connaughton hosts the panel discussion as Brooke Ford of Leviton Network Solutions breaks down prevailing fiber optic and transceiver technologies.
Bring up Brooke Ford, Director of Product Management at Leviton Network Solutions, based in the Fuquay Arena facility outside of Raleigh, North Carolina. Specifically, he runs the product management for fiber cable and connectivity, where he's responsible for portfolio strategy and bringing valued fiber solutions to data center and enterprise customers. He has over 25 years of experience in technical roles in telecom, data center, cable MSO, and U.S. federal government markets. And most importantly, he is my boss. So speak well of me, all of you. I would appreciate it. Brooke's going to talk about emerging technologies ranging from new fiber types to transceiver deployments.
Yeah, thanks, Mike. So if we take an example, Jonathan talked about reference architectures. Tried to pull an example here from NVIDIA, where for their SuperPod, they essentially have and break these down into what they call scalable units, which is essentially 8 racks with 32 nodes for each scalable unit, and they can put 4 of those scalable units together for a SuperPod. So you end up with about 32 racks, which, in terms of data center doesn't seem like a lot, but for these AI networks to connect the compute and the storage and the in-band and the out-of-band, that generates, particularly if they are going to bring those back to a central location, which is one of the reference architectures that NVIDIA specifies, that generates tens of thousands of fibers and thousands of MTP connectors in a very small space. And data center operators, may only have 1 RU or 2 RU to make all of these connections for an individual rack. So these networks are just requiring significant scale and a very high density to make those connections. So one solution that's coming and emerging on the market now, and Jonathan alluded to this, are very small form factor connectors, and in particular, the multi-fiber version of these small form factor connectors. So there's 2 leaders in the industry right now. Senko, their connector they call the SNMT. US Connect calls their connector the MMC. Unfortunately, those 2 connectors are not compatible with each other, so you're either deploying one or the other. But if you look at the physical properties of those connectors, the small form factor connector is definitely much lower profile and actually a little bit skinnier. And really what this enables you to do is triple the density that you would get from a traditional MTP connector. So for our patch panels today that are considered ultra high density, you can get 72 MTPs in a 1 RU footprint. Well, with the small form factor connector, that goes to 216 connectors. And these are, at least initially, 16 fiber connectors. So if you do the math, that equates to 3,456 fibers in a single rack unit, which is pretty staggering. Now, not every customer is going to require that, but as these networks continue to get deployed, they continue to grow, this is going to continue to be a challenge. Now, there are a few considerations as well in deploying these connectors, and they're just emerging technologies, and vendors in the industry are working to solve these. But you have to think about the fact that if you're going to put 216 connectors in a single rack unit, right, your port access, your finger access to those ports is going to be more challenging. You have to consider the fiber management because you don't want a rat's nest to be able to even access these ports. So that becomes very important on how you manage the fiber within the panel. Labeling certainly becomes an issue. You're just limited in real estate space on the front of these panels with 216 connections. So port labeling becomes important in how you go about doing that so you can keep track of where those connections are going and just operationally maintain the network. And then with it being so new, availability also becomes an issue as manufacturing needs to ramp up to support the amount of volume that's out there and the demand that's in the industry. Okay, so that's more of a near-term solution. The small form factor connector, they're just coming on the market now. They're starting to get deployed, but there's also some solutions that are a little more longer term to help handle fiber density. And one of them is multicore fiber. So if you think about a strand of glass today, you have a 9 micron or a 50 micron single core in that strand of glass. Well, Multicore fiber, as the name implies, has multiple cores within that strand of glass, and it can be 2 or 4 or even up to 8 in that single fiber. So if you think about it, let's say you have theoretically an array cord that's 12 fibers, it's 3 millimeter. Well, if you put multicore fiber in there, now you have 40 is what's equivalent of 48 fibers in that same 3 millimeter cord. Okay, so you can see the potential that you would have with this technology. Now, it is today, at least primarily, and is starting to get deployed in submarine networks, and they run small fiber counts in those cables and run dense wave division multiplexing across them to get up the bandwidth. So there's still development to be done just in terms of the cabling itself to be able to put multiple multi-core fibers into a cable. But fortunately, it can be spliced. You can put connectors on the end of it, but it does require very special devices to be able to terminate this fiber. So it's something called a fan-in, fan-out device where you need to take, let's say, 4 cores and split those out individually into individual fibers to actually put a connector on it. So those processes still require some maturity. They can also be very lossy. Even though this is starting to get deployed, there certainly are still some challenges to make it more mainstream or very commercially applicable for a data center. It's very costly. Talked about the loss budget, particularly in that connectivity, and the processes to actually make those connections need to become a little bit more mature. Okay, then we talked about power consumption and how that's going to continue to be a challenge in data centers. And one of the major draws of power are the optics and the transceivers that are in the switches. And there's been a lot of work going on in the last couple of years in the industry to find ways to reduce the power consumption of the optics. So there's 2 technologies here that I'll talk about. The first one, which I'll say is a little bit more longer term because there's more work to be done here, but it's called co-packaged optics. And so if you think about an Ethernet switch, you have an ASIC, right, which is driving the data and the signaling within that switch. And then you have that data traveling across an electrical trace on a PCB to get out to the transceiver itself. And the transceiver is where that signal is then cleaned up, it's amplified, and then it's converted to an optical signal to send that down the optical path or the optical channel. Well, what co-packaged optics does is it takes that functionality of the transceiver and actually pulls it back into the ASIC of the switch. So essentially, it enables you to eliminate the transceiver altogether. Now, you definitely get some benefits out of doing that. You can improve the loss performance of the signal because now you've eliminated the electrical trace on the PCB, right, which is inherently lossy. It's also a lower latency solution because now you've eliminated components within that optical path, and it has a promise of as much as 30 to 50% reduced power by eliminating that transceiver. The challenge is that, number one, it's very complex. It's very proprietary. There's multiple vendors working on this, and they have their own ways of doing that. So you'd be locked into a vendor. And there's a lot of maturity still to happen with thermal considerations and manufacturability and testability and reliability, probably most importantly, because if you think about it, if you lose an optical channel right in the ASIC, right, how do you replace that, right? What is your mechanism? You can't replace the entire Ethernet switch. So you really need to make that a very reliable connection. So there's still a lot of work to be done for this technology to become mainstream. Now, as I'll say maybe an interim step to that, there's other work going on in the transceiver itself to reduce the power consumption of that. And that technology is called linear drive pluggable optics. So it is attempting to do something very similar to what co-packaged optics does. But in this particular case, you're still maintaining a transceiver. You still have a pluggable module that's on the front of the switch, but it is taking one of the most power-hungry devices within the transceiver, which is the digital signal processor, and getting rid of that on the transceiver. So by doing that, you're not completely removing the transceiver, you're not pulling everything into the ASIC, you're just removing one component of it, and that by itself could potentially reduce power consumption up to 20 to 25%. The other benefit of this approach is that, anytime you have transceivers, you're trying to standardize on the interface those transceivers, and they develop what's called multi-source agreements or MSAs to provide that standardization. And there is an MSA that's been put together by a number of different companies for these linear drive pluggable optics. But this too still has its own challenges. As you're removing that DSP, you're now reducing the performance in some form or fashion of the transceiver. So you're going to be limited in terms of the reach for these optics. Technology that needs to mature, very similar to the co-packaged optics in terms of thermal and manufacturability, and the volume is not necessarily going to be there as well. I think the last projection that I saw from Light Counting, who's one of the leading research firms in optics deployments, they're projecting about a 10% volume of all transceivers to be the linear drive pluggable optics. So it's still going to be fairly low compared to traditional transceivers in the industry. Okay, and then finally, I'll touch on latency. And obviously, reducing latency in the network for your point-to-point connection is of prime interest for AI and machine learning networks. And another technology that's been worked on for quite a long time, but really hasn't been widely deployed, is hollow core fiber. So if you, again, let's take our strand of glass that we have today, that 9 micron or 50 micron core is a solid core. So it is still glass within that core to enable the path of light from one end to the other. Well, with hollow core fiber, as the name implies, just like multicore, that is not solid glass. That is actually open space, and it's a hollow core of fiber, which acts similar in properties to a vacuum. Light's going to travel fastest in a vacuum, and with hollow core having those similar properties, the transmission of that light is faster. So in a traditional solid core fiber, you can get about 5 microseconds to travel for a kilometer. In a hollow core fiber, that reduces to 3.3 microseconds. So it's 46% faster in the hollow core. Okay. Now, hollow core fiber also can be spliced, and it also can be terminated, but it, again, like multicore, requires very, very specialized techniques to be able to do that. It is also very lossy. So continued challenges in hollow core. It's very, very high cost. Multicore is more expensive than standard fiber. Hollow core is like orders of magnitude more expensive than standard fiber. So it's very costly to manufacture, and certainly is not being produced in high volumes today. Also, most of the cables that have hollow core tend to have lower fiber counts, right? Which, we need more fiber, in the data center. So it's going to be very specialized in terms of where it could get deployed. And then, of course, I mentioned the lost budget and the connectivity processes. So still has a lot of potential, but there's still things to work through from a development perspective to make it a little bit more mainstream. Now, despite those challenges, another benefit of hollow core fiber in terms of the latency is actually you can expand where you put your data centers and still maintain the same latency footprint. Microsoft obviously saw a lot of value in this because they acquired a company called Luminicity, which was one of the leading vendors and leaders in the development of hollow core technology. And one of the reasons, which they've actually present at some trade shows, is this expansion of footprint. So if they can extend, where they put their data centers and the radius of where those data centers are when they connect it by 2 to 2.5 times, then the cost of the land in those more rural areas is less. The cost of power in those areas is less. And so they're getting a tremendous amount of savings by doing that, which offsets the cost of the fiber itself. So that's, one application. And they continued to work with the folks from Luminicity that they acquired, again, to make this technology a little bit more mature.
Beyond Bandwidth is a podcast series produced by Leviton Network Solutions. For more information on the topics we talked about today, as well as other enterprise or data center network infrastructure content, or to check out all available episodes of Beyond Bandwidth, visit us on the web at leviton.com/beyondbandwidth, or wherever you normally listen to podcasts. If you enjoyed this episode, we'd appreciate you leaving an honest review in your podcast application. Along with word of mouth, leaving a review will help others find our show. I'm Roy Chamberlain, and this was Beyond Bandwidth. Until next time.